I come from a family of scientists. My father was a physicist. My grandfather was a physicist as well. My mother was a psychologist. And so I grew up in this atmosphere of science and research in my family. And so I was always interested in primarily natural sciences, so physics, mathematics. And then when I was growing up, also computer science came to the fore. And I started to see that computer science can be reapplied in a number of different scientific domains. And so I started getting interested in that more, and then I kept pursuing that line of work and interests. I guess also that goes back to my upbringing in some sense, because my father worked for the Polish Academy of Sciences in Poland, and he had a very interesting work environment where he conducted mostly research. He worked also with PhD students, but he didn't do any teaching. And so that was an environment that appealed to me because although I enjoy working with students, I don't enjoy teaching that much. I was looking for a place where I could do research, and the research that I wanted to pursue in distributed systems and high-performance computing systems without being tied down to a tenure-track faculty appointment where teaching would be expected. And ISI does bring me that kind of opportunity to do the work that I like to do, and in a very research-focused environment. At that time, I was a postdoc at UCLA, so I was familiar with the work that was being done at ISI, in particular at that time in the area of grid computing, where you harness the power of distributed resources to do a number of different, to solve a number of different problems. So I certainly knew about the work, and I was interested in that aspect. I also had, through collaborators, I knew people at ISI as well at that time, and that were working in the areas of compilers. And so I interviewed at ISI, talking to people in the compiler group, but also in the distributed computing group, and that's where I started. So we're developing compilers for next generation computing architectures, and that work was, and Mary's doing that work now at the University of Utah. And so we're looking at different types of processor architectures and how compilers can adapt codes to these new types of computing architectures. And so that was the work done at ISI at the time. So a compiler takes a code that's generated by a programmer, which is a high-level, in some sense, high-level description, and maps it down to the instructions that are on a processor. So it does that type of level of translation of what the human provides the computer to what the computer can understand. There are tons of these applications. I mean, basically any code that you write goes through some form of translation down to the hardware. In my own work, we actually use the concept of compilers when we develop high-level workflows that are compiled down to the computing resources. So they're not compiled down to the actual hardware, but they're compiled to the level that you can submit a job to a particular system. So, for example, the Pegasus workflow management system takes a high-level description of a workflow, which has, for example, the scientist can say, we want to do an FFT on a particular file and generate the results. So this is a very simple example. But the Pegasus would take that high-level description. It will look at what resources, compute resources, the scientists have available to them, then look at where the data is for that computation, stage it potentially to that resource, invoke the FFT, the appropriate code on that system, and then give the results back to the user. So this is, again, an example of a compilation of high-level translation from a description to something that can be executed on a resource. I do work with people from different parts of the country and the world, and different disciplines as well. So in computer science, I collaborate with folks from RENSI, which is an institute at the University of North Carolina, University of Notre Dame, Indiana University, Utah University, Texas Tech, and many others, Also folks from University of Tennessee. So a number of, and I'm sure I'm missing some, but so a number of computer scientists, but also work with a number of domain scientists in a number of science areas. So I work with seismologists here at USC, but I also work with gravitational wave physicists that work at Caltech, University of Syracuse, people in Italy. So that's really a large collaboration. In terms of computer science, I also work with folks from the University of Vienna. So that's a recent collaboration. We're looking at the application of workflows in quantum computing. So that's a new area for us that we're looking at. I have longstanding collaborators with people from University of Manchester, looking at issues of managing workflows and scheduling and the task onto the various distributed resources. It's a little bit hard always to describe your work because you're a bit in the weeds of it, but I would say that we aim to automate the computational work that scientists do so that they can focus on the methods and the science rather than how to execute these computations on particular resources. So that we provide the tools to do this translation from what the scientist wants to do to something that will execute at scale, so across a number of different resources, so many tasks, for example, executing in concert across different machines, and accessing potentially terabytes of data to do the computation. When I started in 2000, scientific workflows were not really a big area of research. There was some preliminary work in that area. However, I think with the work that we have done, we really pioneered a lot of work in that area, looking at workflow scheduling aspects. So how do you efficiently take what usually is a graph that the user describes to us and schedule it efficiently on the resources so that the scientists get the results in a short amount of time. We also looked at issues of reliability so that when things break during the computations, the system can recover as much as possible. We also looked at areas of provenance, so that was also an area that was developed and was very active in the, I guess, late 2000s, where you basically, when you give the results to the user wants to be able to interpret what actually happened. So we can allow the user to trace back through all these computations that have happened automatically back to the beginning. So what data was used, what codes were invoked, so that the scientists can easily interpret the scientific value of the result. So is it really the result is something that is correct in a scientific sense? The biggest thing I've ever been part of is the LIGO's first detection of a gravitational wave. I started collaborating with them almost from the very beginning when I joined ISI. So I was part of a Griffin project that was funded by NSF, and LIGO was part of this project. So that was back in 2001. And we developed the initial prototypes for LIGO to use for their work. So we developed a web page where the scientists could go in. They could say, look at the gravitational wave coming from this pulsar for this period of time, and we're very proud of our work. We showed it to the scientists, and they're like, well, it's not exactly what we want. What we want is really we want to see what's underneath. So the system at the time generated a workflow, a graph that said, okay, if the scientists ask for this period of time. For this particular pulsar, you generate a particular graph of computation that needs to happen. And then we take that graph and we map it onto the compute resources that the scientist has available, and everything is done automatically. So when the scientists, the LIGO scientists and our colleagues saw that, they said, what we want to do is we want to manipulate that first graph that you generate behind the web page. And actually, that was kind of the birth of a Pegasus workflow management system, which we then started focusing on. Okay, so if a scientist gives us this graph, then we looked at the automation from then on. And so we worked with the LIGO scientists for a number of years. In 2009, they were there was a point in which LIGO was testing how well their software would work on analyzing the data coming from the detectors. At the time, they had the first version of the detectors in place. However, they were not very sensitive by design to actually detect the gravitational wave. However, they planned to improve the instruments, and they were developing the software to make sure that when they improve the instrument, the software would detect the gravitational wave. So in 2009, there was within the collaboration, so it's a large collaboration of about 1,000 scientists within LIGO. They detected something coming off of the instrument. And then the question was, is it a real gravitational wave? Did they really detect it at that time? Or maybe something else. And so during a big meeting of LIGO, they opened an envelope to figure out whether that was a gravitational wave or not, and turned out that at the time that was a what they call a blind injection. So there was a fake signal that the scientists put in the data to make sure that the software would pick it up. So, it's like Grammy Awards or the Oscars, you open up the envelope and it's like, nope, that was a fake signal. So that was, in a sense, it was disappointing because it was not a real gravitational wave signal, but it did show that if there were a signal coming in, a true signal coming into the detector, the software would pick it up. And that software uses Pegasus underneath to do the automation. So we're very happy about that. But then we had to wait another 6 years, or a little bit more, to actually see Pegasus in action and helping detect the actual gravitational wave. So that was back in 2016, I believe, that LIGO improved their instruments to the point that they were sensitive enough to the gravitational wave to see the gravitational wave signal. And the scientists worked for a number of months to confirm that it was a true signal. They used Pegasus to automate the computations that they needed to do across a number of different computer resources that were funded by NSF. And yes, indeed, they were able to confirm with a high level of certainty that they detected a gravitational wave coming from the collision of two black holes. So that was very exciting for us. We knew it was coming before the announcement because we're part of a collaboration. So we were very excited that our software was used in that way, and that the work that we've been doing since 2001 to 2017, so 16 years of working together, really came to such incredible discovery. So I think that was like one of the biggest things for us. And then, of course, the LIGO scientists received a Nobel Prize for the work, which was, a cherry on top. So, so we're very happy about this, and we continue to collaborate with LIGO and the scientists to this day. So this has been very fun and fruitful. There's always a tension because we're trying to build a software that's general purpose and what some people call it omni-domain. And so we want to have that applicability across a number of domains. However, some scientists have very specific requirements, particularly in terms of scaling the computations or being able to execute the software on different platforms. So where possible to accommodate these, so particularly in terms of execution on different platforms, we try to accommodate it and build the software in a way that it's modular enough that they can use different parts of the software for their work. But that also sometimes makes the software more complex. So there's always a tension between catering to one group of scientists versus keeping it generic and manageable. One thing, though, that's very good about working with these different domains is that things that we do and improve the software for a particular domain are applicable to others as well. So a good example of that is working with earthquake scientists from SCEC. They had workflows which were single core type of application, so it's like individual computations, but they had access to high performance computing systems where the applications need to be in some sense in parallel. So they use particular type of execution models to to be amenable for the execution on HPC system. So we developed techniques to automatically collect a lot of these small pieces of a workflow and run it as a big application on a HPC system. And so the work that we've done for SCEC back in like 2005 and a little bit later on was actually used by LIGO in 2016 to do the computations, because suddenly they got access to also these type of high-performance computing resources. And the techniques that we developed in our software for SCEC were directly applicable. So you see a lot of cross-pollination across domains as well. So the software gets better with more people that we work with. A challenging part of being part of my team is that we do a lot of different work. So we're involved in a number of different projects and working with different types of applications all the time. I think also people find it interesting as well, because it's never the same thing. So, what you're doing today would look different from what you do in a month or 2 months. We also have another recent project that I'm very proud of, and it's called CI Compass. It's an NSF Cyber Infrastructure Center of Excellence that works with major facilities, NSF major facilities such as LIGO, for example, and many others. And under this center, we expand our reach even more. So it's not only working with scientists that need workflows, but in general that need cyber infrastructure to do the work. So we work with cyber infrastructure professionals that work inside these major facilities. And so we look at the whole data life cycle, from data ingestion, like at a telescope, to when the data is disseminated to the users or to the scientific community. So in this work, we have collaborators, as I mentioned earlier, from Renzi, Utah, Indiana University, University of Notre Dame, and Texas Tech, who bring their expertise together in these various areas of a data life cycle, so we can provide advice to the major facilities. And I think this work is even more challenging, like I said, because it requires a number of different expertise, more coordination across various groups. But it's also very rewarding, because if we can make an impact within a major facilities, that can impact a big portion of the scientists that we serve. I think the time to solution, time to getting the results would be much longer if we didn't exist, if we didn't make that process much more efficient. I think maybe the creativity will be dampened as well a little bit, because our work aims to automate as much of the tedious stuff that the scientists need to do as possible, so that they can focus on things at a more creative level, higher level. So in some sense, I believe if they had to deal with the mundane stuff of automate that we can do for them, then they would not have as much time to spend on the more creative sides and focusing on the science. So I think we do make a difference in that way. The creative process that the scientists go through and the ideas that they generate, I don't think would be replaced by AI very soon. I do think that there is a danger, though, for science from AI, because you can generate these papers automatically. You can generate results automatically, and then the problem is really, can you inspect them to the level that you know that these are true results, and that the paper is really based on true results rather than things that have been made up. So I do think that that's a challenge for AI, and that's why the area of explainable AI is so important. And we're looking at these areas as well in the context of science. We're collaborating with researchers from Argonne National Lab and Renzi to look at these issues and seeing what, when you apply AI techniques in science, to make sure that you can actually explain what's going on. In some sense, the scientists always, a lot of them, think in terms of these workflows or pipelines. So in their mind, they actually do have a set of steps that they need to go through to get a particular result. But the challenge is really to take these high-level ideas and then translate them into something that will make it happen, right? So we are here to make that that translation, to make that happen, and to make it happen at scale. So if you have large data sets or the data sets that are in different places, the workflow management system can take that for you and manage it, send it to the right computational resources and do the computing on your behalf. If things break, the workflow management system will recover, so that the scientists can kind of set it and forget it in some sense, right? So yes. So then I think our job is to make it easier for the scientists to focus on what they want. One thing I want to mention, though, it's that in order to make that happen, it sounds like we're doing plumbing, right? But there's a lot of creative energy and ideas that have to go into our work. So we develop algorithms that make that translation possible. And so from a computer science point of view, this is the exciting part for us, that we're developing new ideas of how to make automation better. So one thing that I can tell you we're working towards, more automation is obviously good, and I think we can raise the level of abstraction at some point in the way that the scientists express what they want to do. But I also think there is a lot of, at least in the near term, there's a lot of potential work in the area of edge and IoT devices. So, we have more and more things that are coming online, more sensors that are being deployed everywhere. And there are also scientists that, have a few sensors that they're deploying in the field, for example, and they don't have access to the expertise that the major facilities have, or projects such as LIGO. So I think for us, working on technologies and solutions that will enable individual scientists to gain insights from their work in the field. So you can imagine in ecology or others where they develop, put in sensors to measure different values. I don't know what they do, but they measure the temperature or look at soil moisture or other things, and integrate that knowledge that they have with the knowledge that's collected by major facilities such as NEON. Putting this together in an automated fashion might be something I think that would be useful in the future. So really looking at how you plug in these smaller devices and individual scientists into a bigger scientific ecosystem. If we live in a world where everything is connected, then you have data coming from all over the place. As an individual scientist that want to explore the issues of climate change or food security or other types of items, how do you connect this data coming to you with additional data or additional ideas that you bring into the table to gain insights and knowledge into the areas that you're interested in? I think the Institute is unique in terms of our organization because it provides the people that work there with intellectual freedom to pursue the work that they want to do. So, for example, I've been able to work on Pegasus and expand my work to other domains and other areas in a totally free environment, right? So I'm able to pursue the type of work that I want to do. I write the proposals to NSF, DOE, or NIH on the topics that are of interest to me. And the Institute enables me to pursue that. And we have also a great business office that manages all the paperwork and all the mundane stuff for me. So I can really focus on what I want to do. I have a freedom to have the team that I want, and I have support from the Institute to do that. I think finding people that really want to do that type of work and stay in research rather than go to industry is challenging today. We are hiring, so it's good, but it's always a challenge to integrate new people into the group and see that everybody works well and are happy with the work. And then the other challenge comes from funding because since we are a self-money institution, I can only build a group based on the funding that I have. And sometimes you have more funding than you have people. Sometimes you may have less funding than you have people. So it's always a balance and a challenge to be able to figure out how to manage the two sides, that you have enough funding for the group and you have the right group. people that work in my group, or how I attract them to the group, we tell them that they can work in a number of different disciplines. So they can have impact, for example, on gravitational physics, where we contributed to the first ever direct detection of a gravitational wave. I told them that they can work with the Southern California Earthquake Center, which developed the first ever physics-based shake map for the Southern California area. And the impact there is that these type of maps can be used by civil engineers to determine to what level of tolerance you need to build the buildings that we see today. So very impactful type of work. You can have impact on the science around climate change because you work with ecologists and enable their research. So there's a lot of potential impact that people can have working in my group. At the same time, we do cutting-edge computer science to enable other domains and to enable that level of automation. So we do contribute, we publish in computer science journals and we go to computer science conferences. But we also have publications in physics review letters and others because the scientists do include us on their papers as well. Also, if people come in and they are research engineers, so they're mostly, they do software development primarily, they're also part of a research process in my group. So they do have acknowledgement on papers in terms of co-authorship. If they lead the paper publication, they'll be first authors. If that's a conference paper, they go to the conference and they present. So that's something that oftentimes people don't have when they work in industry. Right? So if you like that type of work, that's a place for them. I tell people that they're doing very impactful work. So I can give examples of the science that's been enabled by the work that we do. I also tell them that they won't be bored. So, we have a lot of different projects that people can be involved with. And because we have the freedom to pursue different avenues of research, if somebody is particularly interested in applying AI to distributed systems, or they want to work on sensor networks, or they want to work on a particular area, we can include that type of interest in the work that they do. And so I think that makes it interesting for people to be here. If the pandemic taught us anything, it's that it's all about people. So, the coding and, the programs, the Zoom, they're all tools that we need. But if we don't connect at a human level, then we will not be able to achieve anything. And I think a lot of people feel that way. Right now we're coming back and we are meeting our colleagues in person. So I attended one big conference and one in-person meeting recently, and it's just incredible how much people have missed these interactions and how much it affected our creativity and well-being. So computer scientists or not, we're all people and we achieve things because we want to work together.